Hello, and welcome to another installment of Car Supply's online virtual training series. Today we're going to talk about the secrets of becoming a pro technician. My name is Adam Tornator. I am a technical service advisor and instructor for Car Supply, and I will be your facilitator today for this training video. So let's talk about some definitions. All right, definition of a professional is one who makes a living with the knowledge and skills that he has acquired. A pro is one who knows more and is better at performance than his peers, and one who looks and acts in a professional manner while performing. But a professional technician, however, is always in demand and never without work. And as we know by the shortage of technicians that we've had in the industry over the past several years, this statement is very, very true. So if you have the knowledge, the skills, and the tools, you will never be without work. All right, so some of the things you need to be a pro technician. All right, you must have that constant thirst for knowledge of the ever-changing industry that we are in. The HVAC industry, as we all know, changes on a yearly basis. All right, so you have to have that constant want to know more. All right, want to know why, want to know how. All right, that intellectual curiosity. All right, you also must act wisely in all that you do. All right, you have critical decisions that you will make on a daily basis when it comes to equipment in a home or equipment in a building. All right, you must be able to think through all problems as they arise. All right, know the sequence of operation of the equipment in front of you, because knowing that sequence of operation is ultimately going to help you with your troubleshooting and diagnostic skills at the end of the day. All right, and then understanding each component and how it is used in that sequence of operation and the role it plays in the total picture. All right, another critical thing is being able to read and understand wiring diagrams. All right, wiring diagrams are a big part of what we do. All right, a lot of wiring diagrams can actually explain the sequence of operation as you look through the wiring diagram. All right, you must also know your responsibilities. Like I said, you are oftentimes required to make a decision specifically to repair a piece of equipment that could have ultimately a life or death impact on your customer. All right, you must understand when it's safe to substitute components and when it's not. A lot of the controls used in equipment nowadays is proprietary and cannot be substituted with a universal part. You have things like programmed algorithms and timing sequences in these control boards that are not matched by universal controls. All right, and then also in the event a catastrophic event occurs, the last person to have their hands on the equipment is going to be the first one called into question. All right, so you must always be thinking of your own personal safety, the safety of your customer and your company as well, to ultimately determine your actions. All right, so there are all sorts of meters and test equipment out there now. Those are some of the things we're going to cover today. We're going to talk about, testing equipment, tools of the trade, also components of, furnaces and air conditioners and how they work, what they do. All right, we're also going to talk about some troubleshooting, some things to help you with your troubleshooting, as well as system diagnosis. So probably the most critical tool that a technician can have is a digital multimeter. This particular case, we're talking about a volt ohm milliammeter. All right, this specific one is going to have the capability of reading AC and DC volts. As we all know, the industry, the technology in the industry is getting more and more complex. We're starting to see a lot more of modulating products entering the residential field, and with that comes the conversion of AC to DC volts. And some of these units are putting out DC voltages in excess of 500 volts. So ultimately, you should have a meter that is capable of reading up to about 600 DC volts. 600 is pretty much the standard on most meters for AC voltage, so you should also have that capability on the DC volt side. AC and DC milliamps, that's another critical setting. Reason being is a lot of your commercial controls, like sensors for economizers, any kind of fresh air dampers that use, sensors, sensing humidity, enthalpy, things like that. Those types of sensors provide milliamp feedback. All right, so you must also have the capability of reading that. AC and DC microamps, this is another critical one because that is how FlameSense is provided. All right, this is the current that is provided through the FlameSense circuit for a control board to sense a flame, or a control module or ignition module to sense a flame. Now, obviously, you must have the capability to read ohms, all right, because one of the things that are very common in an electrical circuit to test is the resistance through that circuit. All right, and that's what the ohms is going to give you. Capacitance, we all know that PSC motors and compressors all use capacitors. All right, so you have to have the ability to test capacitors. And then frequency is also another critical one. Like I talked about earlier with the DC volts, variable speed technology. All right, a lot of these are based on frequency and the pulse width modulation and pulsing of voltage. Okay, and frequency allows you to read that. All right, and then some other features you're going to want are recording minimum and maximum readings in each of those settings. All right, so on a standard, digital volt ohm meter, again, you're going to want AC, DC volts, AC, DC milliamps, AC, DC microamps for flame sensing, ohms, and then continuity. If you're wanting to check whether or not a switch is closed or open, continuity is a good one for that. And then capacitors and frequency, again, also recording minimum and maximum of those values. Clamp on ammeter, recording minimum and maximum, again, it's a critical one. Measures volts, amps, not quite as accurate on voltage measurements as the digital volt ohm meter. However, these are pretty much more common than the standard digital multimeter. They're a little more convenient for technicians in the field and allow you to clamp around a wire to take your amp readings. These are if you have a meter like this, you're typically going to want a true RMS meter that's going to allow you much more accuracy in your readings. Next on the list, we have a digital manometer. There are single port manometers, dual port manometers. I personally prefer a dual port manometer to measure against atmospheric pressure. That provides a lot less room for error when you're measuring against atmospheric pressure. But digital manometers are going to be used for checking duct static pressure. With ECM motors now, they're a little less forgiving with high static. So static pressure now, especially during a startup on a new system, is pretty critical. And also for troubleshooting purposes, you can use a dual port manometer to check pressure drop across the coil to help determine whether or not that coil is clogged, without having to tear the sheet metal or transition or door off to open the coil up to visually inspect it. These are also used for checking and setting gas pressure, inlet to your gas valve and outlet to your manifold, and also verifying pressure switch points. All right. A lot of the older generation were using tubes filled with water to actually measure the pressure in a bubble in that tube. Uh, don't see too many of those out there, but some people are still old school and like to use them. So every once in a while you will come across one. And then pilot pressure test fittings. This is going to be, you're going to see these more in the commercial world, because a lot of the commercial units still use either spark to pilot ignition or a direct spark ignition. So you may need some fittings to connect to the pilot lines on the gas valve. Now, one of the things to point out with pilots, pilots are typically not metered from the gas valve. The incoming pressure is usually directly outputted into the pilot in the gas valve. So if there is any metering in the pilot assembly, it's going to be an orifice or something like that somewhere downstream from the gas valve. But having these fittings to be able to connect to those are detrimental to diagnostics. Digital temperature meter. This always comes in handy, as you'll see when we get a little later on in the training. We're going to talk about some formulas and whatnot that you can use to help calculate capacity for cooling systems and things of that nature. So having a good, accurate digital temperature meter is another critical tool. Obviously, this one is a digital. They have different types of thermocouples that can be used. Some gauge sets now even come with temperature probes and temperature sensors like this, and multimeters do as well. Pipe clamp sensors. These are accessories to digital temperature meters, even digital multimeters, as well as some of the digital gauge sets now. All right, these are much more accurate to take temperature readings from refrigerant lines, water lines, anything, any type of pipe. All right, has that rounded clamp that allows you to clamp it onto that pipe and put it in the exact location you're trying to put it. And a digital probe thermometer is critical as well. A lot of times you're taking temperatures inside the ductwork, inside a piece of equipment. One thing I will recommend, don't use these for refrigerant line readings. They're nowhere near as accurate as like that Type K thermocouple that we just saw in the 2 slides ago. They're just not as accurate, and it could throw you through a loop. So, but this is good for measuring airflow temperature, things like that. Good dry bulb temperature, up in a room. But if you're taking temperatures from a line set, you try to use a pipe clamp sensor. All right, you can also use a digital probe thermometer as a psychrometer to measure wet bulb temperature. You can simply do this by adding a wet shoestring over the metal probe. And one thing to take into consideration is that when taking a wet bulb temperature reading, it has to be moving. You have to have at least 20 feet per minute of air coming across that wick. because what's happening on that wick is it's actually measuring how the water evaporates off of that wick. All right, and that's the definition of the wet bulb temperature. All right. One of the other critical things is when you're taking temperature readings, make sure you're using the same device to take the readings, because then it takes instrumentation error out of the equation. All right. And when you're taking temperatures in an HVAC system, you want to take the temperatures as close to the air handling unit as possible, because if you take the temperature further downstream, it's not going to account for any losses that you could be losing through the ductwork. All right, so however, if you're trying to diagnose a ductwork problem, keep in mind, whatever you have leaving the air handling unit, if you go to a duct run outlet, you should not see more than about a 10% loss of whatever you're reading. So if you have more than a 10% loss, you've got something going on in that ductwork, leakage or insulation, something of those values that is taking place and causing an issue with the ductwork. Refrigerant gauge sets. All right, this is probably the number 2 most important tool that a technician can carry. All right, used to be you have to carry 2 different gauge sets. You used to have to carry one for R22 and a separate one for 410A due to the oil differences that each refrigerant uses. Now R22 used to use the mineral oil, and 410A uses POE oil. However, if you have an R22 system with a newer compressor that was replaced within the past several years, there's a very good possibility that it may be a POE oil system. So always check the oil on the data tag that's in the system. But digital gauges have become pretty much the bread and butter, simply because of the fact that they support multiple refrigerants. It is acceptable to use them with different refrigerants. However, they request that you use different hoses based on the refrigerant that you're using. But let's be honest, who's going to do that? But they also want you to flush them when switching between refrigerants. Some of the refrigerant service tools that we're going to talk about, low loss fittings. These are kind of a personal preference. Some people don't like the squirt of refrigerant when they're taking their hoses, putting their hoses on and off the system. I for one, I personally prefer the hoses with the ball valves, simply to be able to isolate each hose from the gauges. But again, that's just my preference. But you also have to have a good deep vacuum pump. Vacuum pumps have become very, very, very strong in the HVAC industry. However, if a vacuum pump is used properly with the proper size hose, you could have an entire 5-ton system pulled down below 500 microns within a 15-minute period. So again, size correctly, maintain properly, proper hoses. That reference that I just made with the 5-ton unit, that was actually on a 5-ton system with a 3/4 inch vacuum hose and Schrader's removed. That system was pulled down to just over 300 microns in a matter of 15 minutes. So keep that in mind. But typically, while talking about a vacuum, we should definitely be talking about a micron gauge, because micron gauge has become the standard in pulling a vacuum on a system. All right, it doesn't matter whether it's digital or analog, you have to have one nowadays. All right, and you should have a range of 50 to 9,000 microns. Allen wrench bits, there are several different Allen wrench bits that you're going to need to have. Always good to have those on hand, depending on whether, especially if you do commercial work. If you do commercial work, you're going to be using Allen wrench heads quite a bit. But also, if you're not aware, the pressure port on a gas valve, the Allen head size is the same as your liquid service valve on your condenser. So if you have the refrigeration ratchet, that little tool, as long as you have the room around the gas valve, that same tool will work for your gas valve ports as well. Pin pushers. This is kind of an optional deal. However, they are very, very handy. Most equipment nowadays uses several Molex plugs in the systems, and these pin pushers will allow you to remove a damaged pin set in the Molex plug and be able to replace it and install it back into the Molex plug. So if you have a wire harness repair that has to be done, these are a great tool for that. A lot of the manufacturers now, like for a furnace, all the wire harness actually comes in just one big wire harness kit, and they can get very, very expensive. So the furnace components we're going to discuss today are transformers, igniters, pressure switches, pressure transducer, flame sensor, control board, inducer motor, blower motor, limit switches, rollout switches, gas valves, orifices, burners, and gas manifolds. So we'll start with transformers. A transformer is an inductor. All right, it either reduces or increases voltage, and the voltage change is determined by the number of turns in the windings in the transformer. All right, they're typically rated in VA, which is volts times amps. Just a quick note on a transformer. A short on the secondary side is always going to result in a failed primary winding. And the reason for this is because the primary winding always has a lesser rating of amps on the primary side. All right, as you can see here, this one's rated at 0.33 amps on the primary side. However, the VA, this is a 40 VA transformer, so to find the amp draw, all you do is take the 40 VA, divide it by your secondary voltage, which is 24, and that gives you a 1.67 constant amp rating. All right, so anything over that 1.67 over a short period of time, you're either going to blow the transformer or trip the circuit breaker on the transformer if it has one. Hot surface igniters, all right, they're typically silicon carbide, silicon nitride. You should typically see a 40 to 400 ohm resistance value at room temperature, and typically require a 17 to 20 second warm-up period. And as we talk about this newer equipment, a lot of the newer equipment has its own self check mode on the control boards, and you can access these, and it will actually go through component by component through a testing series to make sure each component is working. However, the only one that it can't get feedback from or anything like that is going to be an igniter. Obviously an igniter is going to be a visual test that the technician will have to monitor while it's taking place. So knowing that sequence of that self-check diagnostic feature is critical, so you know when to keep your eye open for that igniter. Okay, flame sensor, otherwise known as a candle rod. These things, guys, these things don't wear out. I know people tend to replace them quite often, but they don't wear out. I mean, typically the only time you have to replace one of these is if that porcelain somehow cracks or breaks. You can clean these. However, there are some products that you do not want to clean these flame sensors with, specifically sandpaper. And the reason for that is that sand is nothing more than just small particles of glass. And glass is an insulator. So if you get a couple of grains of sand on that flame rod, and it goes into the flame, and the flame heats it up and melts that, it actually insulates that rod with melted glass. All right, so when cleaning a flame sensor, you must use a product like steel wool, or one other product that seems to work really well, but most people probably aren't going to want to use it, are paper money. Believe it or not, the fibers in paper money help clean a flame sensor like no other. So, just a little tip. And flame sensors always have live voltage. All right, so as we go through this next flame sensing segment, we'll explain this in a lot more depth. All right, but every manufacturer applies a high voltage to their flame sensor at all times. Now, I will forewarn you that some manufacturers send more than others, but you're typically going to see somewhere between 60 and 120 volts to that flame sensor. So since we're talking about flame sensing, we're going to go ahead and break down the flame sensing process, because it does happen to be one of the more common service calls that a technician seems to get. And mainly because, a lot of times it's due to a simple lack of maintenance. All right. So when a flame probe or flame rod is mounted down through a burner, all right, it's typically mounted in a position where you see two barriers of the flame hitting the flame sensor. All right, and with that high voltage present on that flame sensor, it actually produces an electrical current through the flame back to the burner or to the ground or cabinet. All right. So this is typically how you'll see the installation of a flame sensor, typically within like a half an inch of the burner or so. All right, you're going to have this tracing back to your ignition module or your control board that's providing that high voltage to the flame sensor. All right, and then somewhere in the cabinet of the unit, you're going to find a ground that goes back to the control board or ignition module. Okay, and as it produces that high voltage to the flame rod, it actually creates a microamp signal, which is a very, very, very minute signal, back through the flame to the burner ground and back to your ignition module or control board. Okay, again, it's AC voltage present at your flame sensor. And again, it can be anywhere from 60 to 115, 120 volts, depending on the manufacturer. Okay, the flame completes the rectifying circuit back to a DC microamp signal. All right, that's why I said microamp microamps is a setting on your meter that is absolutely detriment to your position to be able to troubleshoot these issues. All right. The greater the mass ratio of burner and cabinet to the flame rod promotes that rectifier effect through the flame. Okay, and again, the ignition module or control board senses that DC current. Uh, Even though it is very, very, very minute amount, it senses it through the cabinet or through the ground to prove flame. Typically, this takes place within 7 to 8 seconds after ignition. All right, and again, these are measured in microamps, which is a very, very, very minute signal. As you can see here, microamp is 1/1,000,000th of an amp. All right, so again, it's very, very small signal, but the control boards are sensitive enough to pick this up. All right, typical flame current range is 1 to 4 microamps. For most gas furnace ignition controls for the past 10 plus years or so. A typical 24 volt flame current range is 0.1 to 0.4. All right. This is common in package unit ignition controls and things like that. All right. A good flame signal is typically going to be, right around 3 microamps. That's considered a good flame signal. All right, so what happens if you have reverse polarity in your system? All right, if you have reverse polarity and your ignition module or control board doesn't have the capability of sensing the reverse polarity, you're simply going to get a flame sense error. Okay, because if your polarity is reversed, you are ultimately going to set the neutral leg to your flame sensor. So there will be no voltage present at your flame sensor, which will ultimately result in a no flame sense error. So what happens if you have a grounded flame sensor? All right, you're not going to have that microamp signal traveling through the flame, in which case, again, it will not recognize the amperage and will not recognize proof of flame. So excessive gas pressure is another issue that you could potentially see. Gas valves are not always set to pressure from the factory. Some manufacturers will literally just bump a furnace on, run it through the sequence of operation, and then shut it back down and box it and send it out the door. With that being said, gas pressure must always be checked and set during an installation. All right. Otherwise, you could see an issue like this. All right. This is what we call flame lift or flame blow off. All right. It's where the gas pressure is so high that the flame is actually lifting away from the burner. All right, and what this does actually causes the flame sensor to sit in the flame in the improper position. And now you're not going to get an accurate flame sense reading. All right, so again, gas pressure is critical. All right, you can get a similar issue with low gas pressure, again, because you are changing the position of the flame rod in the flame. All right, so when these are designed by the manufacturers, they're designed for that flame sensor to sit in those conical boundary lines in that flame to have the greatest impact on the flame sensing rod. All right, so if you have low gas pressure, you're going to have a smaller flame, and you're not going to have that exposure to that boundary in that flame. And then contaminants. This is probably the most common one that we see out in the field. Uh, over time, there are products and gases that tend to create a barrier, if you will, on the flame rod, or a corrosion, which ultimately ends up acting as an insulator on the flame rod. However, in most cases, this corrosion or barrier can be cleaned off with steel wool. So when you're taking a microamp reading in a DC scale, it's basically used as an inline ammeter. Okay, um, you just disconnect your flame sense wire or or the wire that connects to your flame sensor. Put one probe in that wire and the other probe on the flame sensor, and that will give you the inline path to measure that microamp reading. Now, a microamp DC to volts DC transducer would be needed if you had a meter that does not have a microamp scale. However, some control boards and some manufacturers out there will actually put a flame current pad on the control board that has this transducer automatically built into the board. All right, so it will allow you and give you a descriptive printout on the control board of the conversion. So in this case, you have 1 volt DC equals 1 microamp. All right, so if you're taking a reading on this control board and say you got a good flame signal at 3 microamps, you'd set your meter to volts DC, and you should be getting a 3 volts DC reading on that flame current pad. And here's another example of the flame current pad being on a control board. All right, and then also notice it gives you the minimum flame sense of 0.5 volts, all right, which would be equivalent to 0.5 microamps. All right, but most systems are going to start erroring out once that microamp signal drops below 1. So just a few things to think about when it comes to flame current. Uh, when you have the capability of measuring the flame sense signal, all right, you're seeing the same information that the ignition control uses for flame proofing. All right, also gives you an idea of what kind of burn you're getting from that flame. In today's furnaces with induced draft motors, simply looking at the flame and thinking that the flame looks good is no longer of any value. All right, because the induced draft furnace makes sure that happens regardless of the actual condition. All right, um, this is typically best if the typical flame current for the specific ignition control is known. All right, if you know the range that you're supposed to have, you can use these values to determine what kind of condition you're dealing with. All right, you will see some variations due to supply voltage, humidity, and things like that. All right, but other than that, if you know what you're dealing with, if you know the ratings and range of the piece of equipment and you can measure it against what it should be seeing, just makes your diagnostics a lot easier. Limit switches. Limit switches are typically a thermodisc type. Unless you come across something very, very old, the thermodiscs have been used for quite some time now. They're not duty cycle rated. All right, so what this means is, multiple tripping will ultimately cause the switch to fail. All right, it has to be replaced with the correct limit. Okay, so it has to have the same exact readings. All right, because otherwise, if you put the wrong limit in there, all these furnaces have to go through testing and have to be listed with certain agencies. And if you put a different limit switch in there or any other component for that matter than what's supposed to be in there, what it's tested with, it voids that listing on that piece of equipment. And then we have a rollout switch, which is very, very similar to the limit switch, typically with a much higher temperature rating, simply because it's much closer to the flame. All right. Rollout tripping is typically caused by insufficient combustion air, but it can also be, a direct result of a clogged heat exchanger and, flame rollout for that matter. Heat transfers through metal very, very easily. So if you don't have the proper airflow coming across the heat exchanger, you don't have the right amount of combustion air, or possibly even a clogged exhaust vent. These are all things that could cause your rollout switch to trip, or even a crack in the heat exchanger for that matter. When you have a crack in the heat exchanger, you have more excess air being entering into the combustion chamber, which causes the flame to burn hotter. All right, but also causes incomplete combustion, which is a whole nother training in itself. All right, so those are some of the things to look out for if you come across a rollout switch that is tripped. The majority of rollout switches out there are a manual reset. All right, and this is typically for safety purposes. So as we move on to gas valves, we're going to start out with the White Rogers Gemini gas valve, specifically because this is probably the most latest and greatest valve. Notice that the pressure taps on the valve are different than what most of you are used to seeing. They are raised ports with internal Allen screws. You simply loosen those Allen screws, and then your hoses slide directly over the port. A 1/4 inch hose slides very snugly over that port with a complete seal and will not leak. All right, slips right over very snugly onto those ports. All right, modulator coils. All right, on a modulating type furnace with a modulating gas valve, you're typically going to have a 24-volt signal to power the valve, and then you will have a DC volt signal that actually commands the position of the valve. All right, so you have the 18 volts DC that powers the modulating coil, and then you have a milliamp signal that actually commands the position. And then you have your gas pressure adjustment screw. Again, some manufacturers do set gas valves, some don't. All right, just depends on how quick they're trying to get the pieces of equipment out the door. All right, but one thing to consider is that manufacturers are located all over the world. There are things like standard atmospheric pressure and altitude that factor into play when setting at the factories. So needless to say, they're not always going to be at the same elevation that you are when you're installing at the location you're installing the furnace, or the atmospheric pressure might be slightly different where you're at versus where the manufacturer is. So therefore, this calls for the need of checking and adjusting gas pressure on every single job. All right, so now we're going to talk about the flow of gas through orifices. All right, so gas flowing through an orifice into a burner actually causes air to be pulled into the burner with it. All right, this is known as Bernoulli's law, but it's also known as the Venturi effect, which is I'm sure is what people are more familiar with. All right, so the faster that stream of gas flows, the more air it's going to draw into the burner with it. All right, so here's an example of a manifold orifice. All right, the gas flow is controlled by this orifice. All right, you're going to have 3.5 inches, which is the standard gas pressure coming out of a gas valve to feed a manifold. 3.5 inches of water column for natural gas, or 10 inches of water column for LP or propane. All right, one thing I do want to point out, I have seen some manufacturers now will require as much as 12.5 to 13 inches be constant to the gas valve to guarantee normal operation. All right, so always check your installation manual to verify the pressure that you're supposed to have at your manifold. All right, so as you can see by this illustration of the orifice, you have your standard manifold pressure coming into the orifice, but then you have a smooth transition going down to your orifice opening. All right, if that transition is not smooth, you could experience a very annoying whistling sound from your burner orifices. Now, the length of the orifice tube actually determines the spray pattern of the gas exiting the orifice. All right, so a correct tube length in an orifice should be somewhere between 1/16 of an inch to 1/8 of an inch. Too short of an orifice results in too wide of a spray pattern, and not enough primary air is drawn into the gas stream. And LP contains much more BTU content per cubic foot than natural gas does. All right, so ultimately this causes it to require much more combustion air than a natural gas furnace was. All right, this is why we see greater manifold pressures, because it needs to be able to pull in that extra combustion air. All right, so naturally, with this being said, it causes the burners to be noisier than what they normally would be with a natural gas supply. All right, but this pressure helps keep the LP, that's heavier than air, in a homogeneous mixture with the air. All right, keeps it from falling out of that burner. This also requires a smaller orifice for the proper BTU input. So if you put an LP orifice next to a natural gas orifice, you'll notice that the hole or the opening in the orifice is much smaller on the LP. One of the nice things about in-shop burners is they virtually require no air adjustment, and they're very easy to maintain. I mean, you can pull them off, pretty much rinse them off, wipe them down, and put them right back. That's one of the benefits. But this illustration here is just a picture showing the fixed slot between the orifice and the in-shot burner to where the air is pulled into the burner for the proper air to fuel mixture. And before we jump into pressure switches here, I just want to make a point. The air fuel mixture coming through a burner is very, very critical to the successful ignition of the furnace. LP kits occasionally will come with spoiler screws that must be installed on a burner. I just want to reiterate the critical use of those, because that is what drives that air fuel mixture in the burner for proper combustion. Okay, so if you see spoiler screws in your LP kits, please make sure you install them. Okay, so on to pressure switches. Pressure switches come in all shapes and sizes, many different applications, if you will. The majority of which are normally open switches and close at a specific pressure point. Typically, these pressure points are labeled on the pressure switch themselves. However, if it's not listed on the pressure switch, you're going to need either the installation manual for the furnace, or a piece of equipment, or even the specifications to find out what that rating is. Using a manometer in line with the pressure port, it will also give you an indication of whereabouts that pressure switch makes or breaks. All right. And the typical tolerance with a pressure switch is 0.1 inches of water column. Typical hysteresis is 0.13, and what hysteresis is the lag of air movement. So just like you have lag with Wi-Fi or anything like that, you also have lag with air movement through a pressure switch. All right, so that tolerance is typically 0.13 inches. When checking pressure switches, you're typically going to check it with a meter to see if the switch is open or closed. Unless you suspect some sort of combustion or induced draft issue, at which point you might connect your manometer in series with the or tee your manometer into the pressure switch port to try to determine what pressure your switch is making or breaking at. Now, pressure transducers, on the other hand, are typically used in modulating furnaces. They will actually communicate pressures directly to a control board. All right, and how this is done is it is typically fed a 5-volt DC signal, and it will convert using a pressure tube to the pressure switch circuit, and communicate the pressure back to the board using a 0 to 5 volt DC signal. All right, and you can check these with a voltmeter that reads DC volts. Do not use an ohm meter, because an ohm meter actually provides a voltage out to try to read resistance. All right, and it could ultimately cause the failure in the control board. The reason for pressure transducers being used in gas furnaces is because when you have a modulating furnace, a lot of times that furnace will modulate so far back and so down low that it would actually cause the pressure switch to drop out. In which case it needs some sort of confirmation that the system is still exhausting to keep the burner running. So this is what the pressure transducers are typically used for in furnaces. And now that we've gone through the furnace components, let's take a look and break down the components in an air conditioning system. We're going to talk about compressors, contactors, capacitors, fan motors, reversing valve, accumulator, charge compensator, otherwise known as a quigulator, condenser and evaporator coils, filter dryers, defrost controls, and sensors. Compressors are classified in two different ways, the type of compressor and the method of compression. The types of compressors you'll see in the HVAC industry are open compressors, semi-hermetic, and fully hermetic compressors. Today we're gonna mainly focus on fully hermetic compressors because that is predominantly what you're going to see in the industry. Method of compression is typically how we refer to the compressors themselves, whether it's a reciprocating compressor, a scroll compressor, a rotary compressor, screw compressor, or a centrifugal compressor. Now, screw compressors and centrifugal compressors are typically very large industrial type compressors. You will see those typically on the commercial side of the industry in chillers and things of that nature. You won't see those in any residential applications. So hermetic compressors are completely enclosed in an airtight shell, typically made of stamped or formed sheet metal. The motor is directly connected to the compressor. All right, so the compressor comes in two pieces. All right, the motor is installed in the bottom piece, and then the top piece is welded on and shipped out the door. The terminals are external through the shell of the compressor and are air and moisture tight. And no compressor can provide good performance in all conditions. This is why we have different types of compressors. All right, the compressors are designed specifically for specific conditions or a specific range of conditions. All right, things that have to be considered when selecting a compressor is going to be the suction pressure, discharge pressure, superheat of the suction gas, and discharge gas temperature or discharge superheat. All right, so let's break down the typical compressors that we see in residential applications. Reciprocating compressor is more often referred to in our industry as tin can compressors. Um, these have pistons and valves that create the compression inside the compressor. So it works very similarly to an automotive engine. All right, has pistons, valves, connecting rods, piston rings, uh, and they compress through cylinders that are in the compressor. All right, the next is going to be a scroll compressor, which uses scroll plates and a discharge valve. All of these we'll go through in a little more detail. But then we also have the rotary compressor that uses dividing vanes and an exhaust valve. All right. So let's start with a scroll compressor, being that that's probably the most popular compressor out there. All right, the scroll compressor operates by oscillating two scroll plates. All right, and with these two scroll plates, it can compress up to 8 separate pockets of refrigerant simultaneously. And down through the middle of those scroll plates is the crankshaft. All right, so the crankshaft is mounted vertically through the compressor. You typically have one scroll plate stationary, the other scroll plate is mounted to the crankshaft. And a lot of times when you have a mechanical failure in a scroll compressor, it's typically something in the crankshaft that breaks. Okay, reciprocating compressor, like I talked about, very similar to like a car engine, uses connecting rods to connect the pistons, All right, and then the pistons are going to isolate the oil from the refrigerant compression. And then the rotary compressor works kind of similar to the scroll compressor. All right, but instead of using scroll plates, as you can see by this illustration here, it uses a crankshaft down through the center, vertically down through the center of the compressor, and has a suction vane that opens to bring the suction gas into the compressor. And as the crankshaft rotates, it compresses and pushes that gas out through the discharge valve. Rotary compressors and scroll compressors are typically the compressors you're going to see in the higher end modulating type systems. However, scroll compressors have become very, very common in just about all units from entry level all the way up to the premium levels. When troubleshooting electrical issues with compressors, it's often necessary to take resistance readings on the compressor windings. All right, when doing so, disconnect the wires or rubber plug from the terminal connections on the compressor. Ohm out each winding to each other and ground. And then also, once you're done with that, reconnect the rubber connector or the wires and take the same readings on the other end of the wires so you can trace out whether there's a problem with the wire harness connection or possibly even the wire connections themselves. And if you have a compressor that won't start, some of the things to check are going to be the unit wiring. All right, make sure it's at some point somebody didn't somehow reverse a couple of the wires on the compressor or at the contactor. Obviously, you want to check the voltage at the compressor, check the wire size to the unit. We tell you to check the wire size to the unit because it is very common that a contractor will go in and upsize a piece of equipment without replacing the electrical circuitry to the equipment, and very often is it happen where the existing electrical wire cannot handle the current that the new unit functions at. So what this ultimately does is when the compressor goes to try to start up, that primary voltage will drop down and not be high enough to start the compressor. All right, also check the breaker panel, make sure the breaker didn't trip, and check your run capacitor and start components. Just for reference, 60% of compressor warranties returned have no issue found. So taking your resistance readings on the compressor, this is what you should see. From common to run should be somewhere between 1/2 to 3.5 ohms. All right, run to start should be equivalent to should be the equivalent of common to run plus common to start, and common to start should be 3 times what common to run is. All right, compressors are also going to have a locked rotor amp rating and a rotor loaded amp rating. All right, the rotor loaded amp rating is typically what you're going to see when there is a full load on the system. All right, your locked rotor amps, that's typically what you're going to see if you have a locked up compressor, all right, or some sort of mechanical failure inside the compressor that does not allow the rotor or the crankshaft to turn. Typically, the failure in this is some sort of failed bearing in that crankshaft. All right, and let's talk about just some electrical formulas here, just to remind everyone. Ohm's law. All right, amps times ohms will give you your volts. Volts divided by ohms will give you your amps. Volts divided by amps will give you your ohms. Advantages and disadvantages of hermetic compressors. There's no shaft seal required. It's a completely sealed system, and the oil travels with the refrigerant, so there is no need for a shaft seal to keep the oil on the crank. All right, it's a much more compact compressor assembly and costs much less than an open or semi-hermetic type compressor. Now, the disadvantages to hermetic compressors is that it's not internally serviceable, which means should the compressor fail, the entire compressor must be replaced. And like I said, on the reciprocating compressors, the motor's connected to the crankshaft. The crankshaft is connected to the pistons with connecting rods, and then the piston rings seal the discharge side of the piston from the suction side. Okay, so now let's talk about the electrical circuitry in an air conditioner using start components. All right, so if you have an air conditioner or a heat pump that has a start assist system, so typically this involves a start relay as well as a start capacitor. All right, so the start relay, the way it's designed to work is it on compressor startup, the potential relay is energized and provides that extra leg of power to start the compressor. And once it senses the current draw of the compressor on that circuit, the potential relay drops out and the compressor continues to run through the run circuit. All right, so just something to point out here in the start relay, you're typically going to read a higher than applied voltage there, all right, because it's designed to give it a boost to start the compressor and then it drops out of the circuit. All right, some hard start kits actually come with the potential relays already built onto the start capacitor. All right, which makes it much easier for a technician to install with a simple 2-wire connection. All right, this typical 2-wire connection is typically connected to the common and Herm terminals for hermetic compressor on your run capacitor. This particular brand is a Kickstart brand. All right, Kickstart uses a potential relay in their capacitor. All right, and is also approved by all compressor manufacturers. Like we talked about with meters, you need the capability of reading capacitance. All right, run capacitors are rated in microfarads and voltages. All right, typically you're going to see either a 370 volt capacitor or a 440 volt capacitor. All right, replacements must be the exact same microfarad reading, and they can, however, be a higher voltage. So if you have a 370 volt capacitor, you can put a 440 volt capacitor on there and be okay. But just make sure that your microfarad rating is the same. All right, and then also if you use multiple capacitors and wire them in parallel, it adds microfarads, so it's accumulative. All right, so you can take a 15 microfarad capacitor and wire it in parallel with a 5 microfarad capacitor, actually becomes 20 microfarad circuit. So if you ever get in a bind when you're out on a job and you don't have that specific 35 microfarad, you can use multiple microfarad capacitors to accumulate to your 30. And there's typically a plus or minus 5 to 6% variance on capacitor to let you know that it's good. Contactors are next on the list. These are duty cycle related. However, they should be replaced about every 5 to 7 years. Because what happens is over time the silver gets blown away from the contacts. Most of us that work in the field or have worked in the field, we've come to know this as what we call pitting of the contacts. All right, you can check the coil with an ohm meter, checking the resistance through the coil to make sure the coil is good, or you can also check for 24 volts on the coil with a voltmeter. In other words, it's just a high voltage switch is all this really is. In this next section, we're going to talk about the refrigeration system. All right, we're going to break down all the components in the refrigeration system. We're going to break down piping, other components like accumulators, dryers, and reversing valves. We'll go through each one of those and what they do. So first things first, let's talk about an orifice. All right, an orifice, the opening size is determined by the outdoor unit and indoor coil combination. All right, so be sure to consult the specifications for equipment matching, before installing the product to make sure you got the right one for your application. These are very, very rarely used anymore because with efficiencies they've gotten to now, most cases they require a TXV to achieve those efficiencies. All right. However, there still are a few manufacturers out there that still use fixed orifices. Thermostatic expansion valves, on the other hand, are becoming more and more common in the industry. All right. Again, like I said before, the higher efficiencies that we're achieving and the efficiency mandates that are being put on manufacturers in the industry now are requiring the majority of systems out there to require a thermostatic expansion valve. What this thermostatic expansion valve does is manages the superheat in the evaporator. All right, it takes pressure readings and temperature readings, calculates superheat. All right, and they've got 3 different pressures that apply to the valve to manage the position of the valve. You have the bulb pressure, which is nothing more than a refrigerant inside a copper bulb that varies based on temperature. All right, just like any other refrigerant. All right, that applies pressure through the top of the valve down on the diaphragm against the valve pin. You have a spring pressure, which is a predetermined spring installed in the expansion valve in the valve body. All right, this is otherwise known as the superheat spring. All right, then you've also got evaporator pressure coming from your equalizer tube that goes over and taps into your suction line. All right, these 3 pressures work to drive that expansion valve to the position that it needs to be in. expansion valves can come already pre-installed on an evaporator coil, or they may be sold as a separate accessory to an evaporator coil. Obviously, the pictures that we're using here are old, being that you're seeing a copper tube and fin coil. Most coils now are all aluminum, but again, just this is more just for reference to the expansion valve. In this particular case, this is a complete bolt-on accessory. Typically, when it's purchased as an accessory, there is no brazing required, and it's a 100% complete bolt-on. So when installing a TXV, all right, first thing you're going to do is relieve the holding charge on the coil. All right, remove the liquid line fitting, and note that the fitting has right hand threads. All right, this is critical. You don't want to cross thread the fitting. All right, and always use a backup wrench. You're dealing with some pretty small copper tubes, and they can be broken off pretty easily. All right, you just want to hand tighten the nut and then give it an additional quarter turn max. All right, and here's another example of the accessory installation, where you have your equalizer tube that comes over and connects to a pre-installed service port on the suction line, and then you have your two nuts that connect to the TXV body, one going to your distributor assembly side and then the other going to your liquid line assembly. So now let's talk about bulb location. All right, bulb location is not as critical on a horizontal plane as it is on a vertical plane. However, it still does have specific locations that they have to be in. Okay, so for 3/4 inch or smaller, you can be 12 o'clock position is typically the best position. All right, you don't want it on the bottom, because if you have oil passing through the system, it can create a barrier on the bottom of the copper and not give you an accurate temperature sensing reading. All right, so anything larger than 3/4, you can put that in a 4 or 8 o'clock position, typically like the 45-degree offset. All right, and again, you don't want that on the very bottom, because oil sits in the bottom of those copper tubes and can create a barrier for temperature sensing. When the bulb is installed in the vertical position, the thing you have to keep in mind here is that you are using refrigerant to sense temperature. All right, so there is refrigerant inside that bulb. Well, when you have the refrigerant, you've also got oil. All right, so you want the pigtails in the upward position so that the oil cannot clog your capillary tubes from your bulb back to your expansion valve. All right, because the whole purpose of this bulb is to exert pressure on the top of the diaphragm to drive the expansion valve to the position it needs to be based on the suction temperature that it's on the outlet of the coil. So an oil clog in that capillary tube could deter your TXV position from being where it needs to be. So now let's talk about superheat. All right, after a liquid is changed to a vapor, any heat added to the vapor raises its temperature. All right, this is a sensible heat change. As long as the pressure remains constant, the resulting vapor is superheated. Superheated vapor is a vapor whose temperature is above its boiling or saturation point. Using superheat has to be done on any unit with a fixed restrictor. All right, so what that means is any unit that uses a fixed orifice or capillary tubes to regulate the flow of refrigerant into a coil you'll have to use a superheat method of charging. All right, unless for some reason you know the total charge weight of the system. If you know the total charge weight, you can just weigh the charge in and call it a day. But if you don't know the total charge weight, you must use the superheat method to charge that system. Now, subcooling, on the other hand, is any liquid that has a temperature lower than a saturation temperature is subcooled. And this is typically what we see nowadays with most of the equipment using TXVs. You're typically going to use a subcooling method to charge unless for some reason you know the total charge weight or you have the charge calculator for the refrigerant line size that you have. The Quiggulator, or charge compensator, if you will, most of us know it as the charge compensator, is nothing more than a storage container that stores excess refrigerant on a heat pump. All right, works similarly to an accumulator. All right, but it's literally just a receiver that stores excess refrigerant. All right, so the cooling mode typically requires the use of more refrigerant. Refrigerant in the heating mode, the requirement isn't as much, so that extra refrigerant is stored in the charge compensator. All right, this was named after Stan Quiggle, who was a Coleman engineer that invented it. All right, and notice that you do have a suction line and a vapor line and a liquid line that goes into this compensator. So how the charge compensator works: in the heating mode, the outdoor vapor line running through its center is cooler than the liquid line. Warmer liquid is drawn into the Quiggulator. Any vapor in the shell condenses, causing the Quiggulator to be full of liquid refrigerant. In the cooling mode, on the other hand, the outdoor vapor line is now warmer than the liquid line. Liquid refrigerant is driven out into the system. Only vapor remains in the shell of the Quiggulator. An accumulator, on the other hand, is similar. However, this is a place for excess refrigerant to sit. All right. This also protects the compressor from liquid slugs of refrigerant that could be present in the suction line when entering or leaving a defrost cycle. Liquid is returned to the system through the oil return port and second port, higher on the suction line. So now we're going to break down a reversing valve and how a reversing valve functions. A reversing valve in the heating mode, the solenoid coil is typically not energized. This is what we consider an O-type valve. However, there are a couple of manufacturers out there that do energize in the heating mode, and most manufacturers' reasoning behind this is they want the valve, if it fails, they want the valve to fail in the heating mode to where the equipment can still provide heat. All right, so how the shifting works in the reversing valve is pressure is applied internally to the valve body by a pilot valve. All right, this pilot valve uses the discharge pressure to shift a plunger inside the valve body. All right, so uh, based on what mode you're in will determine how that pilot valve shifts using a solenoid valve. All right, so the solenoid valve shifts the pilot valve, which in turn drives the discharge pressure to shift the plunger in the reversing valve. So troubleshooting, the easiest way to troubleshoot a reversing valve issue is by knowing how the reversing valve works and taking a temperature drop across the valve. All right, you should. This is an older. Older slide. I have seen. Uh, I've seen recent temperature differences of 15 degrees and the unit be okay. All right, so but anything higher than 15 to 20 degrees, that you've got an issue with that reversing valve not positioning right. Um, I know this slide says 7 degrees, but again, this is an old slide, and this applies both in heating and cooling modes. All right, so the temperature test is the best way, other than testing the solenoid coil for the pilot valve, because that is a mechanical device. All right, an electrical mechanical device. So you can check to make sure that you have voltage at the solenoid, and you should be able to tell which way that, or which position that reversing valve should be in. All right, so in this case, we're in the cooling cycle where the pilot valve is shifted. Looking at this diagram, we are discharging discharge pressure to the right side of the valve, shifting the plunger all the way to the left, which allows our indoor unit to, our indoor suction line or vapor line to come back and then go directly to the suction line on the compressor. Okay, so as I told you in the beginning of the training segment that I was going to offer you some training, or I'm sorry, some formulas to help you calculate cooling capacity. All right, um, these formulas can be used in the diagnostic process to help you determine whether or not the cooling capacity is being achieved by the equipment. All right, so let's start out with the total BTU content. All right, this can be found by having your CFM rating or your operational CFM of the system. All right, if you multiply that by total heat content 1 minus total heat content 2 times 4.5, this will give you your total cooling capacity of the system. All right, and I'll explain total heat content in just a minute. All right, the sensible capacity equation is going to be your CFM times temperature 1 minus temperature 2 times 1.08. All right, and temperatures reference dry bulb temperatures. Then your latent heat equation is going to be CFM times W1 minus W2 times 0.683, and W references specific humidity, which is grains of water per pound of air, as you'll find on a psychrometric chart. All right, and this is all based on standard air at 13.3 cubic feet per pound. All right, so when we were talking about total heat content, we have a chart that converts wet bulb temperature to total heat content. All right, so you can take wet bulb temperatures and convert them to total heat content based on tenths of a degree. All right, and that will factor into your total heat content, as you'll see here in just a few minutes when we start going through some diagnostics, that how that applies to your total heat content differential. All right, but using those formulas will help you determine the output BTU of a cooling system. All right, and this table is pretty lengthy, could result in multiple pages. All right, so now as we're getting ready to head into our diagnostic system, we're going to take a look at your typical refrigeration circuit. All right, a typical refrigeration circuit is going to have four main components. You're going to have the compressor, which we consider basically the heart of the system. All right, and everybody at this point in their career as a technician should know that a compressor is a vapor or gas pump. It should not be pumping liquid. All right, but your four components are a compressor, a condensing heat exchanger or coil, an evaporating heat exchanger or coil, and a metering device. All right, a metering device is what's going to meter your refrigerant to help the refrigerant change state and absorb heat. All right, so how the system works: the compressor pumps out a high temperature, high pressure vapor, which goes directly into what we call the discharge superheat region of the coil. All right, and this is typically the top section of the condenser coil. You get to the midsection of the coil, which becomes your condensing saturation region. All right, and then you get to the lower section, in which case by the time you get to the lowest section of the condenser coil, your refrigerant will be all liquid. All right, and that is considered the subcooling region. All right, and what this allows us to provide a solid column of liquid refrigerant to the metering device. All right, the metering device then meters the refrigerant down to a part vapor, part liquid mixture into the evaporator saturation region of the evaporator coil. All right, and that is predominantly 75% of the coil. All right, and in which case it goes into the evaporator superheat region, which converts, after all the heat added to the refrigerant from the airflow passing over the coil, converts the refrigerant back to 100% vapor. So if you ever have liquid coming back to your compressor, you have a problem that you need to get to the bottom of. All right, from which case you have 100% superheated vapor going back to your compressor from your evaporator coil. All right, we have a lot of different diagnostic forms out there. I have them in a spreadsheet form like what you see here on the screen. I also have them in more of like an illustration form where you can actually see all of your readings in their locations on the refrigeration circuit. For some people, it helps making the diagnostic process a little simpler, and we all like to see pictures, so it tends to make it a little easier on the eyes instead of a bunch of numbers just running together. So here we're actually just going to use the Excel spreadsheet form of diagnostic form so we can use it for an example in our training today. So in this case, we're going to use a 3-ton unit with a flow rater or a piston or capillary tube type metering device. All right, In this case, we're going to have a suction pressure of 75 pounds, suction line temperature of 54 degrees, an outdoor dry bulb temperature of 85 degrees, entering dry bulb temperature of 74 degrees, that would be entering the evaporator coil, and then a leaving dry bulb temperature of 56 degrees. We have a 215 pound liquid pressure, 100 degree liquid line temperature. All right, suction saturation is going to be 44. All right, based on our pressure reading and converted on our gauges. All right, which gives us a total suction superheat of 10 degrees. And with our liquid saturation being at 107 degrees based on our 215 pounds liquid pressure, we have a liquid line temperature of 100 degrees, which gives us a 7-degree subcooling. All right. Discharge pressure, discharge line temperature, and discharge saturation. These can be found on the discharge line directly leaving the compressor. Typically your discharge pressure is going to be a little bit higher leaving the compressor than it is at the liquid line service valve, simply because you're running through a coil before you get to the liquid line valve, so your pressure is typically going to be a little bit higher at the discharge area. So a lot of times there aren't service ports on the discharge pressure, so it's hard to get that reading. But in this case, we have one, we've tested it, we're 215 pounds, 175 degrees, which 215 gives us a discharge saturation of 107, which gives us a 68-degree discharge superheat. All right, so on the enthalpy side, this is where our equation comes in. All right, this is where our formula comes in. So the entering wet bulb temperature going into the coil was 64 degrees. Okay, leaving wet bulb temperature is 54 degrees. All right, and converting these numbers on the enthalpy to wet bulb, or wet bulb to enthalpy conversion chart, gives us 29.31 for 64 degrees and 22.61 for 54 degrees, which gives us a total heat content drop of 6.7. All right. Electrically, we have 236 volts and 15 amps on the system. So overall, looking at this picture, this is an R22 system. Overall, looking at this picture, this unit is completely fine. All right. This is a correctly operating system. All right, and the process that we saw in the refrigeration chart is taking place exactly the way it should be. All right, so now we're going to do one, again, still with an R22 system. All right, but this one we're going to find a problem in. All right, so we're still using the same system, the 3-ton 10 SEER with a fixed orifice. All right, we have a 49 pound suction pressure, an outdoor dry bulb temperature of 89 degrees. We've got a suction line temperature of 70 degrees, a suction saturation temperature of 26 degrees, giving us a 44 degree superheat. Our entering dry bulb temperature to the coil is 78 degrees, and the leaving dry bulb temperature is 68 degrees, giving us only a 10 degree drop through our evaporator. Our liquid pressure at this point is 168 pounds. We have a 90 degree liquid saturation temperature and a 90 degree liquid line temperature, giving us 0 degrees of subcooling. Our discharge pressure is the same as liquid pressure, and our discharge line temperature is 214 degrees, and discharge saturation is 90 degrees. Guys, anytime you run into a system with a discharge line temperature approaching 200 degrees, you have a problem. And ultimately, that high of a temperature is ultimately going to cause the oil to break down in the compressor and cause the compressor to fail if you don't get to the bottom of the issue. All right. So with that being said, we have a discharge saturation temperature of 90 degrees and a discharge superheat of 124. Our entering wet bulb temperature to the evaporator coil was 66 degrees, converting to 30.83 degrees total heat content. All right, the 61 degree leaving wet bulb temperature converts to 27.15, which gives us a differential of 3.68. All right, so clearly we can see that we've lost capacity in this system. This is the same system we just looked at on the previous slide with different number inputs. So clearly we can see here that we have an issue. The issue that we have here is an under system. All right, so this is what you can expect to see. Now these same characters apply to 410A, just with higher pressure readings. So the same characteristics apply. So let's do another one. All right, same system. Now we have 49-pound suction. Suction line temperature is 26 degrees. Suction saturation is 26 degrees. We have zero superheat. All right, outdoor dry bulbs 81, entering dry bulb is 74, leaving dry bulb is 48 with a delta T of 26 degrees. All right, liquid pressure is still 168 pounds. Liquid saturation is 90. Liquid line temperatures 82, giving us a subcooling of 8 degrees. Discharge pressure is 168. Discharge line temperature is 144 degrees. Discharge saturation is 90, giving us a total discharge superheat of 54 degrees. All right. Our entering wet bulb temperature was 62 degrees, converted on our total heat content chart to 27.85. Leaving wet bulb was 47 degrees, converting to 18.68 on the total heat content chart, giving us a differential of 9.17. All right, so there is two numbers here that really tell us what's going on in the picture. The fact that we have a 0 degree superheat and a 26 degree temperature drop. This ultimately tells us that we don't have enough airflow across the coil. All right, your typical temperature drop on a cooling system is right around 20 degrees. All right, now in some cases in extreme temperatures you could see as little as 18 degrees, but for the most part you should be somewhere around 20 degrees. All right, but also the 0 degree superheat was the other giveaway that we didn't have enough airflow. All right. So this is what you were seeing happen. All right, so basically we were missing the extra section of the evaporator, so the entire evaporator was just being used as a saturation region. All right, so we are still getting a part liquid back to the compressor in this scenario. All right, so now let's take a look at one that has a TXV. All right, so in this case we've got a suction pressure of 58 pounds, outdoor dry bulb 9 degrees, suction line temperature of 70 degrees, suction saturation temperature of 32 degrees, giving us a 38 degree superheat. All right, our entering dry bulb is 78 degrees, leaving dry bulb is 65 degrees, giving us a delta T of 13 degrees. All right, our liquid pressure is 239 pounds, our liquid saturation is 114, and liquid line temperature of 95 degrees, giving us a subcooling of 19 degrees. All right, discharge pressure is 239, discharge line temperature 200, discharge saturation 114, giving us a discharge superheat of 86 degrees. All right, our entering wet bulb was 64 degrees, converting to total heat content of 29.31. Our leaving wet bulb was 57, converting to a 24.48 total heat content, giving us a differential of 4.83. In this case, this is indicating that we have a restricted TXV. The TXV is not opening to the position to allow the flow of refrigerant all the way through the expansion valve. So to see this visually, all right, we've lost part of our evaporator saturation region because our metering device is not metering properly. All right. The next thing we're going to cover is microchannel coil technology. Microchannel coils are you're starting to see them more and more, predominantly in commercial, but some manufacturers use them on their air conditioning condensers as well. So let's go through and we'll break down how a microchannel coil works and the components in them. All right. Now, microchannel coils are 100% aluminum coils. All right. They are what we call a two-pass coil system. All right. So they are constructed just like a radiator in a car. They have very, very narrow passageways, which means they can be repaired without losing much efficiency from the coil itself because of all of the passes in the channels. All right, so there are rows of channels, as you can see here by the illustration, that have aluminum clad fins between the channels to help disperse heat. All right, and microchannel coils are built on they have a much greater heat transfer process. They transfer heat a lot better than your typical tube and fin coil, and typically allow for a much smaller footprint in a unit. All right, we'll talk about that a little more when we get to the advantages and disadvantages of these coils. All right, but one of the other things I want to point out, with it being a two-pass system, all right, so basically you have half of your coil moving refrigerant in one direction and then half of your coil moving refrigerant back the other direction. All right, so what happens here is with that being the case, you actually have a header on each end of the coil. All right, and in those headers are baffles that direct the flow of refrigerant to the channels that they're supposed to go to. I have on a few occasions seen where those baffles in those headers have broken off and create a restriction in the coil. So just something to be on the lookout for. All right. Just a couple of quick notes. Again, it is the same technology used in the automotive industry on radiators. Currently only available on air conditioner models that I'm aware of. They are currently in the process of designing to be used on heat pumps and evaporator coils. However, I've been told that the issues that they've been having with getting them to work with heat pumps and air conditioning coils is drainage. With that clad style aluminum fin, you don't have a straight drag path to a drain pan. So drainage is currently the issue with using them in those applications. So some of the advantages, like I said, they have a much greater heat transfer efficiency. in smaller coils as compared to tube and fin. They don't require as much refrigerant. All right. Uh, you don't require much refrigerant in the entire system. It has a greater corrosion resistance as opposed to copper because of it being all aluminum. And quite frankly, the aluminum construction and the clad design of the fins give the coil a more rigid and more strength than the tube and fin style. All right, so typically, if you were to try to pick up a tube and fin coil, it would be trying to bend all different sorts of ways on you. All right, a microchannel coil doesn't do that near as much as the tube and fin style coils. Now, the disadvantages, on the other hand, with the fact that it can't hold the capacity of refrigerant, if you have an issue in the refrigeration circuit, it's highly likely that you are going to have to recover refrigerant because you cannot pump the unit down because the coil does not have the capacity to hold the entire system charge in the outdoor unit. All right, so unfortunately, that is the disadvantage, but the advantages far outweigh the disadvantages. And that's going to complete our training for today. I hope all of this information was beneficial to you all. And as always, you can feel free to reach out should you have any questions or concerns or comments that you'd like us to have via email or phone call. We look forward to seeing you again soon. Thank you and have a great day.